In the last class, we have seen that orthonormal bases are fairly nice bases in the sense that they behave very much like the regular IJK bases that we're used to, except that they do so in a more general setting, meaning either in higher dimensions or by allowing the use of vectors other than ij and k. What we're going to do in this class is see how we can use this orthonormality property and apply it to other things such as a matrix. So here is how it goes. So we're going to start from the idea that orthonormal bases have nice properties. That's not an easy word to say, is it? And also we're going to consider the fact that in regular Euclidean spaces, so spaces that consist of regular vectors, each basis, be it orthonormal or not, may be organized in a matrix. In fact, we can take the vectors of a basis and we can place them either as rows or as columns, and we're going to come up with a matrix. Of course, it's going to be actually a square matrix. For what we're going to do today is we're going to place those basis vectors as columns. No particular reason we had to choose it. I'm choosing it to do it as columns. Given this arrangement, we're going to go back to looking at this matrix and saying, well, how can we mimic the properties of an orthonormal basis now that we have a look at a matrix? So what we're going to do is we're going to say that an n by n matrix is orthogonal if its columns form an orthonormal basis. Now, big warning here. Notice that there is a bit of an inconsistency in this definition, right? We're going to say that a matrix is orthogonal if its columns form an orthonormal basis. So we say that this matrix is orthogonal if its columns are not only orthogonal to each other, so dot product equals 0, but also if their length is equal to 1. Let's look at this definition from a slightly different perspective to see what these orthogonal matrices look like. Okay? So A is an orthogonal matrix if and only if what? Again, remember, the columns have to form an orthonormal basis. What does that mean? It means if I take the dot product of any two columns, I should end up with 1 if I is equal to j. So if I'm taking the dot product of a column with itself, or 0 if I is not equal to j, which means I'm taking the dot product of two different columns. That sounds familiar, right? Because in fact what that means is if I compute the product of the transpose of A times A and I look at the ij element in this product, what am I really doing? I'm taking the ith row of A transpose times the jth column. Well, that's the same thing as taking the ith column of A times the jth column of A, right? And again, by that definition, that means that this is equal to 1 if I is equal to j, and 0 if I is not equal to j. But we know a matrix like that. We know a matrix whose elements are 1 on the diagonal when I is equal to j, and 0 when it's off the diagonal when I is not equal to j. And of course, that's the identity matrix. So what have we found out? What we found out is that we have an orthogonal matrix. The product of A transpose times A is equal to the identity, which means that A transpose in this case is actually the inverse of A. And so that means if we're dealing with orthogonal matrices, computing the inverse just is done by simply transposing the matrix. Therefore, orthogonal matrices can be seen as those square matrices whose inverse is the transpose. So the fact that the inverse of an orthogonal matrix is just its transpose is a very nice property. Besides, again, all the columns form a nice orthonormal basis, so everything is fine and dandy. But there is another side of the coin, and it has to do with the entries that make up an orthogonal matrix. So they're nice from the point of view of properties, but they look ugly, okay? So because given the definition, the entries of an orthogonal matrix have to always be between -1 and 1. Remember, their length is 1. That means that the sum of their squares have to be equal to 1, which means that each one of those has to be between -1 and 1. It can't be any bigger than that. The other thing is that generally this is going to mean that the elements are not going to be nice fractions, but they're going to probably involve some radicals or some strange things, or maybe some even worse kind of situations. So the individual entries are going to look pretty ugly. Okay. So usually it's just a weird looking matrix. There is one situation, however, where things are not that bad, and it's really the simplest case of them all, in which case orthogonal matrices take on a very nice simple form. And that's the case when we're looking at 2 by 2 matrices. So what you may want to ask is, well, what does an orthogonal 2 by 2 matrix look like? Well, yeah, we know it looks like A, B, C, D. What those numbers look like? What kind of properties do they have to obey or fulfill in order for the matrix to be orthogonal? Well, what I would like you to do is start thinking about it. We're going to look at it in class a little bit more, but start exploring it on your own. See if you can find out what properties A, B, C, and D should satisfy, and therefore see if you can arrive at what these 2 by 2 matrices which are orthogonal look like.